almost a straight line up. But we can see that there's a cap here, which will be explained later on when we look at the actual data. Okay. So next, remember all the features that we have in our graph over here. So not all of this will actually be useful in the end. And we can think of how we can combine some attributes in order to create like better versions of what we already have. So some attributes don't make sense on their own, but we can combine them with other attributes to derive greater insights from them. So take, for example, like the efficiency of a tap. If you want to measure this in real life, but we are only given the total volume that the tap has, the total volume of water the tap has given out, and the total time it took for the tap to do so. So both of this, if you look at them on themselves by their own, they're not really useful. If you have a total volume, but in more time, compared to like more volume in less time, the one with more volume in less time will be more efficient. So what we actually want is the rate of water flow. So we can actually combine these two data by dividing the total volume by total time to give us the rate of water flow. And this is more important for us compared to these two values on their own. So this is how these are some of the ways we can combine attributes in order to determine or get greater insights that our model can pick out and use for predictions. So moving on, after we have identified all these patterns, it's great. But we need to know that data is not always perfect, and we sometimes get incomplete data. So any missing values or strange anomalies that could be a result of human error. So what do I mean by missing values? So in the case of a housing district, let's say that some of the data is not available for that point. Maybe you're not able to get the number of rooms in the district in time, and the person that's entering all this data just leaves it blank. Or some strange anomalies that could be a result of human error. So what if the data is outdated and someone just used the past data, and that creates an anomaly? So population rises really quickly, and let's say someone uses the data from the past 5 years instead of the current data. So the population could experience a sharp dip compared to other populations in the district. And this could be an anomaly you might want to sort out. So after cleaning your data, making sure that there's no anomalies, not to say that we don't want anomalies, but make sure that anomalies are accounted for. We want to transform the data into something that the computer can read. So this applies largely to data like textual or categorical data. So what I mean by this is that you have your colors, maybe red, yellow, green. This kind of text, the computer can't actually read them. And we need to transform this data in a way that can be better understood by our model. So in this case, we're doing what's called a one-hot encoding, where we have columns representing the data, red, yellow, and green, and we have ones representing whether it's a yes or no. So for row 1, it'll be transformed into 3 columns, with red being 1 and the rest being 0. And this is an example of some data transformation that we can apply to our data. Another way to transform your data is actually to fill in missing values. So remember the missing values we have previously, or incomplete values? We can actually just fill them in with another value that we want, and that may not affect our final data as much as it would with it being blank. So after this, after messing with all our data and finally getting all the results that we want from our data, what's left is to train our model. So notice that this part comes really late after we have done a lot of work on our data. But this is what is most common in machine learning, is that your data usually takes the most time to prepare, and the training of the model is up to multiple iterations and randomly guessing, mostly randomly guessing. So with our data all prepared, all we have to do is select a model for the task. So most supervised machine learning are supervised in the sense that you have the data with your features and the data that you want to predict. So in this case, the features of our housing districts and the price of the house. These are classified under supervised machine learning, where the labels of the data are available to you. And usually, this can be classified into classification or regression problems. So if you want to know what kind of models you should use, you can go to scikit-learn.com. This is their documentation page, and you can see that there's classification and regression. So under these two categories, you can look at the multiple algorithms that are available here. So if you're trying to do supervised learning on a classification problem, you can actually go here and look at all the models they have and try out all of them and find out what works best on your data. Because multiple models, different models can work differently on different types of data sets. So if you ever need to find out what models you can actually use for your data, you can look at all this over here. Now, moving on. So after we have trained our model, we need to evaluate how accurate it is or how well it performed on our data set. So for this, we need some sort of metric to measure how well a model performs as compared to other models itself. Now, a very good way to demonstrate why this metric is important is in the case of coin flips. So at random, we will get it right 50% of the time. And if your model performs worse than 50%, you might as well have just guessed randomly. So if our model can actually get it right more than 50% of the time, get it right as in guessing the coin, the head or tails of a coin, right 51% of the time, it will be an improvement over our original guessing. And this 50% and 51% is a metric that we use to measure how well our model performs. And we can usually measure this by the accuracy or the error of the model. So in this case, 50% refers to both the accuracy, because you're right 50% of the time, and the error, because you're wrong 50% of the time as well. And it's not always clear cut that the accuracy and error are just like 100% minus the other. Okay, so after we're done evaluating our model, we need to look at how we can improve it. Let's say you obtain an error of 15%. We want to improve our model to reduce this error. And what we can do is we can revisit our previous steps to try and draw greater insights from our attributes. So all the data processing that you've done so far, you can revisit them and look at what else you can improve or what assumptions you may have about the data set that could be wrong. So initially, if you go back to this slide, we can see that we have this assumption that houses near the coastline are likely to be higher priced. But if you look at the top over here, it's not just near the coastline, because the ones at the top here are near the coastline, but their prices are still low. So maybe there's some other patterns or some other attributes for this data that make this higher price compared to the rest. And the distance to the coastline may not be always the right answer. So it's good to go back, look at what assumptions you have made in your data set so far, and see what else you can do to improve upon it. So if you go back to your data and you look at what else you can improve, sometimes you might find out that you just have to try them all. So if you make a change into maybe putting in the data about the coastlines into your data set, and you try and evaluate your model, you get an error of 15%. What you can do next is to just remove that attribute and test it again and see how well it performs. If it performs better, like consistently, you can sort of say that that data wasn't very useful and actually made your model perform worse. So it's a lot of iterations that you have to do. You can keep trying out different models, you can keep trying out different data sets, different iterations of a data set. Or the next thing you do is change to other models. So as shown on the previous page, there were a lot of models for you to choose from, and you can choose any of them and just see what the metrics you get are. But it's important to note that you must measure your metrics accurately. So the method that you choose to evaluate your model must be consistent across all the models that you use. Finally, there are these things called hyperparameters of the model that you can tune in order to improve the accuracy of the model. So this usually gives you marginal performance increase, such that there's not a lot of science around it, and sometimes different attributes, different features or hyperparameters will work better for different data sets. So this method, you really have to just try them all out, but there are inbuilt functions that will help you to achieve this. So this step is a lot of iterations. So what you need to do is you need to keep trying to find out different combinations of maybe your features, maybe your models, or maybe the hyperparameters that you need to tune in order to get the best results possible. And even then, this may not give you the best accuracy, but what you're looking for is something that can transfer well into real life. So after you've done all these improvements of your model, we go back to the test set. So all of these evaluation metrics and everything, you perform on your training set only. Once you're finally ready for a model that you feel is best, you look at the test set and you evaluate your model on this test set that you have. And what this will give you in the end is the generalization error. So suppose after all your training, all your changing and everything that you updated for your model, you obtain an error of 5%. So your model is 95% accurate. Now, when you perform on the test set, it is likely to be less accurate than your model that performed on the training set. So this is because your model has never seen the test set at all. It doesn't know the answers to the test set, and it's likely to perform worse. So this difference in accuracy is what's called the generalization error. And this error just gives you a way to measure how well your data will perform in real life examples, where it's trained when it's asked to predict examples of data it has never seen before. Okay, so that's the end of the slides. And we'll be moving on to the Collab Notebooks in order to walk through the code and give you a feel of what it's like to actually work with a end-to-end machine learning project. Okay, so can everyone switch over to their Collab slides and Collab Notebook if they have it? So the first snippet of code is just some basic setup that you have in almost all the projects that you have. These are some of the common imports and the libraries that we have seen in the previous workshop and will be used in this workshop as well. So you have your NumPy, you have OS, which gives you functions that can work with your system, matplot library to plot graphs. This is special code that works in notebooks and will display all your plots inline, which is in the notebook itself, instead of opening a new window for it. So this step is also an important one. It's called the seed of your random. So NumPy uses a seed to generate random numbers, which will be used in a lot of our functions later on. And to make sure that the notebook's output is the same throughout runs, you don't want the random numbers to be random through different runs, because it could cause the evaluation of a model to be different on each run and inaccurate in a sense when you compare different models. Okay, and these are just helper functions that will actually make your plot labels bigger and like make it look nicer. So this part is strictly not necessary. Okay, so first off, we'll be getting the data. And as mentioned earlier, we'll be using a housing price dataset for this workshop. And this dataset gives us the pricing of houses in a particular district along with their attributes. So attributes like longitude, latitude that we have seen so far. We'll explore these features and see how they can be used to improve the accuracy of our model. So over here, I know we imported OS twice, but it's fine to do it on Collabs or your notebooks. And what we'll be doing here is just to download the dataset. So this download route is actually the link to the dataset. And we have some helper functions here that will download it into a fixed path in our data, in our system. So it's good to have functions like this over here, because when you go through, when you're done with a project and you want to work on another project, for example, and you need to download data again, you actually reuse these functions across different projects. So we'll start to run all these functions. Yeah. So after running these three code snippets, you realize that there's actually no output because, yeah, there's just no output for this at all. And okay, so they run successfully, and we can't actually see if it's successful or not, but after the next one, we can actually see whether anything has been downloaded. So this code snippet is from pandas, and we also define a helper function here that just reads the CSV file that we downloaded. So over here in housing path, what should have been inside housing path is our path to the CSV file that we downloaded. And what we do here is actually we're asking pandas, we're using this helper function by pandas to read a CSV, and we pass in the CSV file. So over here, we have housing goes to load housing data, which loads all this data from the CSV into a pandas data frame. And this housing actually now refers to a pandas data frame. And in the previous workshop, we learned about the method .head, which actually shows you the first 5 rows of the data set. So as you can see here, this is actually similar to the one on the slide because I just took it from here. And we go through all these columns and we can see what they may actually mean. So longitude and latitude, they just mean to the position of the district on the map. The housing median age is the age of the houses in the district. So the median age of all the ages of the housing in the district. Total rooms are total number of rooms in the district as a whole. So when you look at this statistic, it doesn't seem very useful, right? Because some households may have, some districts may have more houses than the others. And this will cause them to have more rooms at all, more rooms in the end. So like you can see 880 here and 7099 over here. So this kind of seems useless to have in our data set as well, because it doesn't give you any information about that household, that district as a whole. And in fact, it could actually mess with your data set. Because let's say this place has a lot of rooms, but it's due to this district being counted as a very large district. So in the end, it could not be densely populated and instead just be a very large district, which will cause your model to incorrectly take in these attributes as facts. So total bedrooms are the same as rooms, but it's just bedrooms. And the population. So this population gives you the size of the population in that district. So this is in the thousands. So there's 322,000 people in this district. And there's like 2 million people in this district. So this one gives us a sense of how densely populated the district is. And similarly to household, which is very similar to population as well. So these two terms, they are a bit more, they can be thought of as like more important than total rooms or total bedrooms. But we can see how we can actually use these two later on. Next, households. Okay, next, median income. So median income is the most obvious ones, where we can predict that a district with higher median income is most likely to have more expensive houses because people there can afford more. So this one, for now, we'll suppose that this could be like the most important one in your data set. So next, the median house value. So this is actually the label that we want. This is the final data that we wish to predict for this data set. And we won't actually be looking at this much in terms of training our model, but for evaluating how useful each of these features are, this will be quite important. And finally, we have ocean proximity. So this will tell you how far away this district is from the coastline. So previously, we had this hypothesis that houses near the coastline tend to cost more. And we can see whether this will actually play into the hypothesis later on. Also, another thing to note is that this is in textual data and it's categorical. So we need to apply some data transformation to this in the future. Okay, so that's all for housing.head, which gives you the first 5 rows. So if you want to get a quick description of the data, in particular, like the total number of rows that you have, which tells you how many districts you have in the data, we can use this function called housing.info. So this tells you that we have 20,000 rows in our data set. And if you look through all of them, you can notice that total bedrooms only has 20,433 rows that have data inside them. So this is the case of missing data, where some of the data is actually missing for total bedrooms. So maybe there's no strict definition for bedrooms in the district, and we can't actually obtain the data for that. So this is something that you have to take note of and rectify when you're pre-processing your data. Okay, so as we previously noticed, the ocean proximity attribute is likely to be categorical. And we can actually find out what categories exist and how many districts belong to that category by using the value counts method. So this is a method for pandas data frames, and you can actually use it to obtain the possible values for ocean proximity and how many of each category there are. So we can see that for ocean proximity, they can be less than 1 hour away from the ocean. They can be inland. They can be near the ocean, near the bay, or they could be island, which is very far away from the coast. So you see that these are the counts of how many districts fall inside each of this range. And we have to work to transform this later on. So this is for categorical data. For numerical data, we can use describe to show a summary. So similar to what value counts does, describe shows us some quick statistics on the data we're working with. So this only applies to numerical data, and it's not very useful for other data, like textual and categorical data. So also, note that not all of these features will have anything useful for us. So the average longitude and latitude is most likely not going to be very useful to us because it just tells us the middle of California. The median housing, the mean of the housing ages is actually quite important because we can get a feel of how old these districts are. So 28 means that most of them are around like 28 range, and you can look at standard deviation to look at the range. So maybe you can give a guess that most of them are between 16 to 40 years of age. And these are the rest of the data, and we won't actually go into detail for this, but we can. It's just good to have a feel of what your data set is like before you actually try to pick out some patterns among them. Okay, so this code snap, it actually prints out it actually plots out all your data in terms of their frequency. So these are the values of their data, and these are the frequency, which we saw previously. And we actually went through this already, but this is how you do it in code, which is to show a histogram. The bins means the categories they'll be split into. So each of these like lines is actually just a bin, and figure size just gives you your figure, the size of the figure. And you use plot.show to show your plots. Okay. So before we start, we want to split our data to a training set and a test set. And we'll set aside the test set, and we won't actually come back to it until we need to evaluate our model in the end. So there are multiple ways to do this actually. So one way you can do is you can generate random numbers for 80% of your data and pick out those indexes as your train set and the rest will be part of your testing set. So this is actually like a very common thing you need to do in data science. So what sklearn does, the scikit-learn library, is they provide you a function to split into train and test. So using this train test split function, we actually give our data set housing, the size of the test that we want, and the random state. So this random state acts similarly to numpy.random, the seed for numpy.random, which is that your train and test split will be the same throughout different runs. So let's say you select rows 0 to 8 for your train and 9 and 10 for your test. When you run this function again, it'll give you the same indexes that were used for train and test, so that on different runs, you get the same data set. Okay, so we'll run this and we can see the size of each training set. So our training set actually has a length of 16,512, and the test set has a length of 4,128. So this is about 80-20. Okay, so there's actually a problem with this data. It's the fact that we chose it randomly, and it may not represent it may not correctly represent what our data set should be like. So remember we had this, where 9,000 of them are 1 hour away from the ocean, and only 5 of them are very far from the ocean. So what we want is for our data set to look something like this, where the distribution for any category is similar. So we'll choose a very important category that we think is most likely to represent our data set, and we need to make sure the distribution of the data is similar to this. So what I mean by this is that you can see that 1 hour away from the ocean, this contributes about 40% of the data set. So in our train and test set, we must make sure that the number of rows or number of districts that are less than 1 hour away from the ocean contributes about 40% of our train set and 40% of our test set, to create an equal distribution that is likely to be accurate towards like our final data. So I'll give you an example of what we mean. So this is how we actually do it. We'll look at the histogram for median income, because as we noted earlier, this is likely to be the most important part of our data and something that's the most correlation with median house prices. So we can see that we can actually split this into 5 categories. Okay, so from 0 to 2 is one category, from 2 to 4 another category, from 4 to maybe 5.5 over here is another category, and then 5.5 to 6, and anything above 6. And we can split into these 5 categories that will give us like something similar to our ocean proximity categories. So we create these beans, which are from 0 to 1.5, from 1.5 to 3, from 3 to 4.5, and from 4.5 to 6, and finally anything above 6. And we will label them 1, 2, 3, 4, 5. So what this line of code does is that it creates a new column inside your data set. The housing data set that we have, we'll create a new column called income category, and we'll cut it based on the median income of the data set. Okay. So as you can see, if your median income is greater than 6, you'll be placed in label 5. So your income category here will be 5. If your median income is from 5 to 6, so between 4.5 and 6, you'll be in category 4, which is 4 over here. So similar to, now that we have this data in categorical form, we can do what we did for ocean proximity and get value counts. So we have about 7,000 in category 3, 6,000 in category 2, 3,000 here, 2,000 here, and 800 here. So we can see that there's not a lot of housing districts that are very low income itself. Now, if you plot a histogram, it should look something similar to this. So we can see that the distribution is somewhat similar, but not totally the same, because we did cut off at 6, and everything above 6 was part of one data set. Okay. So now that we have these percentages, we want to make sure that our train and test split contains these percentages of data as well. And how we can do this is through this function called stratified shuffle split from sklearn as well. So it's the same library, but a different function. So we want the number of splits to be 1, and test size to be 0.2 as well, and we need to set the random state as well. So, okay, so let's just run this function. Okay, so what this does is that it actually splits your data based on these percentages. So we pass in income category because we want it to split on the percentages of this category itself. And so for test set, the number of, we are, okay, so what this line of code does is that we look at the income category row, and we get their counts. So this is similar to what we've done here above, but now we divide each value by the length of the stratified test set. So these are the percentages of rows that have label 3, percentages of rows with label 2, and rows with 4, rows with 5, and rows with 1. So this one is for our test set, and if you look at our original data set, we can see the values are very similar. So 35% here, 31%, 17%, 11%, and 3% over here. And they're very similar in terms of this distribution, which gives us like more confidence to say that whatever we predict on our test set is likely to be the same as what we predict for like the original data set itself. So over here, we define like a custom function. It actually helps you to prepare, calculate some of the errors in your data set. So if you compare the props, so you see, this is our overall percentages of categories with 1, 2, 3, 4, and 5. This is the one for stratified, which is similar to the overall one. But if you use the random the data set that was selected randomly, you actually get 40% here, 32% here, 35% here, 16% here, which is a bit different from the overall data set. And the error is higher than what we have for stratified. So the random data set is a bit different from what we have overall. And this will contribute to an error in predictions, where we think our model might be like more accurate than it should be, or less accurate than it should be. Okay, so now that we have actually split into train and test, we actually don't need this income category, because the model will actually pick up these categories by itself, and we don't actually have to like split it nicely for the model to see. So in our train set and test set, we will drop the income category. So after running this line, we won't have this category inside our train set and our test set anymore. Okay. So now, after we have split our train and test set, what we can do now is to actually play around with our training set and find out what features we want to keep, what features we want to manipulate, and everything else that we'll talk about in the slides. So notice that from here on, we don't mess with the test set anymore, and we are only using the train set. So we don't actually want to just mess around with our original train set. We want to create a copy, which we can like play around, modify, and make sure that the original is available for us to reset if we ever need to. So right here, we create a copy of our data set and set it to housing. Okay. So the first step is to visualize geographical data. And as we've seen previously with latitude and longitude, it's a great idea to create a scatter plot of all districts to visualize data, rather than viewing it in terms of a bar graph like this, or histogram. So we want a scatter graph with X being the longitude and Y being the latitude. And this is actually an inbuilt function by Pandas data frame. So just by running this, we can see that we obtain the same map that we saw previously. And to get the second map, we need to add transparency towards our model. So these scatter points, we want each point to be a bit transparent, so we can actually see the density of points at each area. So the code is largely the same, but there's another hyperparameter that Pandas give you, which is called alpha, and this sets the transparency of your, how opaque your data is. So 0.1 is less opaque, and 1 is totally opaque. So value of 0, you won't even see anything on the graph. So we run this, and we can see that we get the graph as shown in the second one. And it's a bit easier to see in terms of how densely populated each area is in California. Okay, so our brains are very good at spotting patterns of pictures, but there's a lot of parameters that are available to us, like alpha, that we can actually use to get a better plot of this graph. So if you want to find out what kind of parameters that there are inside this, we actually look at the Pandas documentation. If you go here and you search for a plot, you can actually get a list of every single parameter that they allow you to mess with. Okay, so we want to look at housing prices, which is the end outcome that we wish to predict. So we want the radius of each circle to represent the district's population and the color to represent the price instead. And we'll use a predefined color map, which is something that Pandas actually provides. And you can actually get it from like this function over here, which ranges from blue, low values, to red, high values. Okay, so let's walk through the parameters. We want a scatter graph, X being longitude, Y being latitude. Alpha, we put 0.4 here, which is more opaque than usual. So for S, this is the size of each plot, like size of each dot over here. We want it to be the population divided by 100. And the label for this S will be population. This sets the figure size. Okay, so C stands for color. So we want the color by median house value. So the color of the graph is determined by the median house value. And this color map is set to jet. And color bar true gives us a color bar at the side. So if we plot this, we get the graph as shown. So S over here is the size. So larger dots like this have a larger population than smaller dots like this. And the color of each dot is represented by the median house value. So you can see on the right, 500K is darker, red, and 0 is around like blue and light blue. So as mentioned in slides, this image tells us that the housing prices are very much related to location. Like closer to the ocean, you might get better housing price, higher prices, and further away from the ocean, you might get like worse prices. So we can see that population density plays a part in this as well. So you can look at, it's hard to see, but you can see that there are very large circles over here, which represent more dense areas. And as you know, dense areas could drive house prices up, and this could be a reason in having higher housing prices as well. So what this data basically tells us is that population is important, and ocean proximity may be useful as well. But we also need to note that in Northern California, which is up above here, the housing prices in coastal areas are not that high as well. So it's not a simple rule that, oh, near the coastline, higher price. Okay, so how can we actually quantify this and like verify if our hypothesis is correct? So how we do that is we look for correlations. And since the data set is not too large, we can actually compute the standard correlation coefficient, the R value, like +1 or -1, between every pair of attributes. So for all data up here, for longitude, we can compute with everything else, with housing, median age, with total rooms and everything. What this looks like is the following. Okay. All right. So this is the correlation matrix for median house value with every other value. So as you can see, for median house value to median house value, it's 1, because the points are definitely linearly related because this value directly affects this value. So as you can see, median income is like a huge player as well, because the value is close to 1. So this tells us that as median income increases, median house value is likely to increase as well. So where have we seen this before? It's actually over here in our correlation graph. So this is median house value and this is median income. So as median income increases, house value increases as well. So this verifies our hypothesis that median income could be like important in terms of determining what the median house value is likely to be. Okay, so moving on. Remember we had total rooms and total bedrooms. So we can see that total rooms actually is like 0.13, which is higher than the rest, like compared to median age, households, and bedrooms. So this tells us that what we initially assumed could be wrong as well. Because at first we thought that total rooms may not be like important in our data, but it turns out it's actually higher than the rest, which are above 0. And so looking at these statistics can actually help you to like determine which info is likely to be more important. So if we look at the negative values, negative doesn't mean that they're not related. It just means that as the population increases, the median house value is likely to decrease, and maybe like longitude and latitude as well. But as we noted, longitude and latitude, it's not really good to quantify them in terms of like a direct relation towards house value. And maybe something else could be done with this as well. But for now, we'll leave it as this. And we just focus on what we have with total rooms, median housing median age, households and total bedrooms, and population. Okay, so we can actually plot a scatter matrix, which is a graph like this, but for every single point. Okay, so as you can see, for median income and median house value, as median income increases, house value increases as well. And for this info like housing median age, which we saw was a value of 0.11, there's not really a lot of correlation between the median age and the house value. So as this increases, it could increase, it could decrease, and it's hard to tell at this point. So scatter matrices are a way for you to actually visualize this data in terms of like plots. So you can actually look at this, or you can just look at this. And these values are not a very good indicator of like, okay, sorry, give me a second. Okay, yeah, sorry about that. So these values are not 100% indicator of how well they're correlated, and we actually look to the graph to find out if there's any relation we might have missed out. So over here, we see that total rooms, it looks like there's a correlation, but by the shape of the graph, we can actually tell that there's actually not much relation in terms of the graph. So a lot of random values over here, and maybe a slight increase over here, which we don't know the reason for. But this gives us a chance to actually know that there's something wrong with our rooms data, and this might be like a cause of error in the future. It's okay. So this is the same graph, but we plotted bigger. It's median income with median house value. So this is the most important one that we've decided so far. Okay, so what can we see from this graph is that the correlation is very strong. We can see the upward trend. The points are not too dispersed. So very dispersed points, like where points are very far away from each other, could indicate lower correlation compared to points that are closer together. And second, we notice that there's a clearly visible line at 500K. So if you look at the house values of 500K, we can see that there are points there from like 0 to 16 of median income. And this is actually a problem in our data set. So the reason for this is that the original data set, they kept the price at 500K. So anything above 500K, they still counted as 500K, which is not a very good way to collect data. But when you're given this data as a data scientist, these are some things that you need to take note of and like maybe obtain like a workaround for this. So one implication of this is that, let's say that you have your model and the actual problem that you need to predict, prices can go above 500K. So one issue with your model is that your model will actually almost never predict prices above 500K due to this limitation. So if you do need to predict prices for houses above 500K, you might need to remove all this data from the dataset so that it doesn't learn that there's an upper cap on 500K. So there's also like more obvious straight line, less obvious straight lines. We can see that around 450K, there's like a slight line over here, and around 250K, there's another line over here. You see? So this could correspond to like certain caps on different districts that could lead to like a cap on housing prices, maybe due to laws or anything. And we might want to remove this data set to prevent our algorithm from learning these data quirks. Yeah. So after we go through experimenting with attribute combinations, we will take a short break and we'll reconvene. We'll take a short break at like 8 and reconvene like 15 minutes later. So for experimenting with attribute combinations, referring back to this slide, we're actually looking to combine different attributes to obtain greater insights from our data. So what we talked about previously is rooms, bedrooms, and population. So we can see that total rooms doesn't really matter on its own because the size of a district might differ, and this might cause like total rooms to differ. So a better metric is the total rooms divided by households, which gives us rooms per household. Similarly, for total bedrooms, we can divide by total rooms to get more bedrooms per room. So like a house with more bedrooms, we can think that maybe like larger families will like purchase houses with more bedrooms per room, and these larger families might be like poorer families instead, which like have a lot of children. So these are some of the assumptions that we have for our data set, and we can verify whether this is true or not later on. So we can also obtain population per household by dividing population by households. Okay, so after we do this, we can look at the correlation matrix again to find out how like related they are. So with these new values, we can see that rooms per household has shot up to 14% at 0.14, and it's actually above total rooms. So just by dividing this data by household, we can obtain like greater correlation with our median house value. So we can see that population per household remains the same. It doesn't really have any change compared to population. So we can sort of assume that these two data might not be that important to us in our model as well. Now, notice something is that total bedrooms was actually 0.04 at the start, and it's super low value. But after we divided by rooms, it has shot all the way to negative 0.25, which indicates like a certain level of correlation towards our data set, just that it's negative related in this sense. So if we plot the scatter graph of bedrooms per room, we see that as the bedrooms per room increases, the median house value sort of decreases. So, like as mentioned previously, the number of bedrooms per room can indicate like having more bedrooms per room can indicate larger families which are bought by like lower household incomes. So given this, the house values of these districts are likely to be lower than the rest. Okay, so this is actually most of the transformations of our data that we have done up to this point, and we can actually get a feel of what our data actually looks like right now. So now we have longitude, latitude, housing median age, total rooms, and now we have the additional rooms per household, bedrooms per room, and population per household. So these three are the new metrics that have added to our data set. And note, okay, so it's not actually all, and there are actually other columns which includes the ocean proximity that is not shown over here. But for now, what we have, like these are the patterns that we have obtained just by like exploring our data and what we have added to our data set and may help us with our predictions in the future. So over here, we'll take a short break and we'll reconvene at about 8:10. Okay, by the way, if you guys have any questions, you can ask them in Padlet and we'll address these questions after the break. Okay, hi. I hope everyone's back. And before we continue with the second part, we'll answer some questions first. Okay, so first, how do you remove the data, like the caps at 500K, 450K, to prevent the machine from learning this pattern? So, to remove the data, we can actually go through like the pandas data frame, and we can filter out all the rows with a value of 500K for a median house value. So any house with this value, we'll just delete the row. So it's available in pandas documentation that you can actually filter out all these rows that have this value, or filter out rows that are greater or equals to this value. So let me see if I can find something similar. Okay. Okay, yeah, but so over here, you simply have to like go through pandas documentation. You can find out how you can actually filter out by rows that are greater than this value, and then just drop them from the data set instead. Or another thing you can do is just filter for values that are less than this value, and we can actually like obtain them. So it's harder to do it when it's like at 450K or 200K because it's in the middle of all the values. But what you can do is actually you find out this range that occurs within, and then you have to like filter out from there. So there's no like straightforward way to actually remove all this anomaly. Like you can actually like detect them automatically. You need to actually go through a data set, find out like what are these ranges that are anomalous, and then remove them from the data set. Okay. So for data cleaning, if there are missing data, how do we decide if we should remove the data, remove that row, or fill in those missing data? And if we fill in, how should we know what to fill in? Okay, so to add on to this data, so this is true. So if the number of rows are small compared to the total number of rows, then you can sort of safely remove this data because they might not affect your data that much. And it could be like a small change in the distribution. But as always, you should always make sure that the rows that you're removing, there's a reason why this data could be like missing. So, okay, nice, someone has given the function here. But let's say that you have this data set and you have these two values that are at the tail ends of the data. So one is like really high house value, one is really low. So what if the really high house values, they're all missing a certain data. So in this case, it's not really, they could be like a small number of houses with very high values, and they could like be missing some data. And in this case, it wouldn't make sense to remove them because of the fact that it's a small percentage of your data that have like very high house values. And these are data you actually want to keep. But the fact that they are missing values, you can actually fill them in with the mean or mode of other available data. So for that particular row that they're missing, which we'll see later, you can add in like the mean, the median, or the mode. And this will actually like help your model to learn that this feature is like in the middle, and it's not a huge impact in how the pricing should be determined based on this data. So we'll actually see an example of this later on. Okay, so I think that's all the questions for now. And yeah, this is the correct function. So we'll continue with the second part of the slides. The second part of the notebook. So from here on, just to recap, what we've done so far is we've identified some of the attributes of our data that can be useful in predicting the house value of this district, these houses in the district. So for example, we added rooms per household, bedrooms per room, population per household, and these are all the data that we need. So we won't be adding any more new ones inside. We'll just be working with these attributes that we have. So all these features, these are all the features we'll be using from now on. Okay. So the next part is a bit more technical because it's about preparing a pipeline and like ensuring you can reproduce these results and ensuring that your data is perfect to be put into the model. So instead of doing this manually, we'll write functions to do this and allow us to reproduce this transformation on any data set. So when you get a fresh data set, you apply all these transformations through the functions, and we can actually get what we need at the end of these functions. So another thing that's good about this is that we can build a library of transformation functions that can be reused in future projects. So some of these functions like filling in missing values, we actually reuse them in other projects that we use, not just this one. So we can also use these functions in our live system to transform new data before feeding into our algorithms. So what this means is that suppose your data set in real life, you can only obtain longitude, latitude, and all the other like 8 values that we have so far. What we don't have is the price in real life. Like when you have a new house that's built, we can get information on where it is, the age of the house, which should be 0, the rooms of the house, the bedrooms of the house, population of the house, and rooms, bedrooms, and population of the district and households in the districts. So all this data is available to us in real time, in real life, and we can actually transform this data into this category with all these new categories when we have a new data that's coming in. So by transforming this data, we can actually put this right into a model and predict the prices of this of the new houses. So this is mostly for the fact that the data you get in real life may not be the same as the data that you have like right now, or the transformed data that you have. So what this function allows you to do is that you convert this live incoming data into data that can directly fit into your model to get a prediction. And this is actually one of the most important parts in doing data science, is that if you want anything that's to happen live, you need to have a series of transformations for your data that's coming in order to transform into the data that your algorithm needs. Okay, so yeah, having all these functions also make it easy for you to try out various transformations and see which combination works the best. So as mentioned previously, we can assume that like things maybe like rooms per household can actually affect our data. So this is something new that we added, and it may or may not affect our data. We can actually remove this part or edit, or we can actually remove this part later on and see whether it affects our model. And by doing all this like random selection of features that we're going to add in or not, we can see which combination of transformation actually works the best. Okay, so to get into the code, so the first thing we do is we drop the median house value. So this is the value we want to predict, and we actually drop this because of the fact that we want our model to learn how to predict house values without the answers. So we'll put the labels or the answers in another data frame or data set. So housing contains all our features, and housing labels will contain like the answers to our features. Okay, so the first part is data cleaning, and as asked earlier, when we have missing data, our learning algorithms cannot work with these missing features. So we have to create a few functions to take care of them. And note that missing values, you can handle them in 3 ways. So first way is get rid of the corresponding districts. So this one is just dropping the entire row. So if you have this row that's missing maybe households, you just, okay, sorry, this is not a row, but if we have a row above, so any of these rows, if you're actually missing data, we can just drop the entire row. And if this row is missing total bedrooms, we drop the entire row, we continue on as normal, like nothing has happened. And the other method is to get rid of the whole attribute. So this is more of an extreme scenario. So assume that some of your rows, like maybe total bedrooms of a place. So the total bedrooms of a district may be hard to obtain because maybe it's hard to define what's a bedroom and what's not. So maybe this data is more inaccurate, and sometimes people just don't even count it all together. So what you can do is that in these events, you can actually just drop the entire attribute. So we won't even count total bedrooms when we are like feeding our data into a model. We get this data and we just drop it all together. Like we just ignore it altogether. So the last way, which is almost the most common way, we set the value to some value. So we set to 0, we set it to the mean, or we set it to the median. So the mean just means the average. The median means the number that appears the most. So statistically, when you set them to values like the mean or the median, it's not likely to affect your data that much. Because when the data is spread across like a range, the data points near towards the end of the ranges are likely to have like a greater impact on affecting the data compared to the ones in the middle. So assume that if all your data, all your rows, they have this column that just gives 1. So that column is actually useless because since every data set shows 1, it won't help in your prediction at all. So this is what filling in the value to some value like the mean or the median is attempting to do. So it's attempting to replicate the effect. Okay. So sample rows. This one gives us the rows that have any null values. So each housing.isNull will show, it just filters it by null values, and it gives by axis 1, which is by column. So if we look at the first 5 of these rows, we actually get the 5 rows that have no bedrooms at all. So note that previously, only total bedrooms has some rows that are missing. So when we looked at the counts for each of the columns, we can see that only total bedrooms had less rows than the others. So this will be the only data that we'll be handling, which is total bedrooms. Okay, so option 1 is that we can drop the row. So we can housing.drop NA, which is drop any rows that have like NaN values. And the subset that we choose is by total bedrooms. So option 1, which is get rid of the corresponding districts. So option 2, we can drop the entire column itself. And we do that by housing.drop and the column name and x is equals to 1, which is this way. So that's option 2. Now, the most popular option which we will be going for in this project is that we'll calculate the median through a helper function by pandas. And then we get all the rows that are incomplete and we fill them with the median. So sample incomplete rows are the rows that have incomplete values of like total bedrooms. And we just fill them in place, which means that we actually modify the data frame and put in all the null values with median. So after running this, we can see that these rows, 4629 and row 4629 over here, is now the same row, except that total bedrooms is filled in with the median, which happens to be 433.0 in this case. So this is how we can actually handle these values by ourselves. And these are through the helps of like data pandas libraries, which we like chain multiple functions together to fill the values in place. So this is actually a very common thing in machine learning. So scikit-learn actually provides you an option to actually transform your data. So there's something called imputer, which is a class that helps, which is like a class, right? That helps you to handle all these missing values. So it's a very common theme in data science to have missing values, and scikit-learn provides you imputer, and it actually helps you to like fill in all these missing values in a way that's in line with scikit-learn libraries. So we'll see what this means in a second when we define our own custom class, like transformations. So first, we create an imputer. So simple imputer here is actually just a simple renaming of imputer, but because of different libraries and different versions that you may have, we give this code in order for it to work across all platforms. So we define an imputer class, and the strategy we choose is median because we want to fill in the median values. And housing num means we select all the columns that have numerical values. So note that ocean proximity is categorical and it's textual data. So this text data is not what we want, and we can't actually transform with the median in this case because there's no range. So we have to drop this value first, and we only take in the numerical values. Okay, so now this is the important part of scikit-learn libraries. So sklearn, most of their functions and classes, they work this way, where you have the class dot fit your data, and this fit function will actually take this fit function just feeds in your data to the class. So we can think of this as just feeding in data into our imputer class. Okay, so now that we have fed in the data, we can calculate statistics from imputer. So these are actually the median of each row, of each column. So maybe the first one is longitude. We can see that the median is -118. And for bedroom, which is 433. So another way to get the median values is through housing. So okay, this is just a way to compare the median values to make sure that they're accurate. So statistics, this is calculated by sklearn's library. If we calculate through pandas, we actually do it this way, which is .median, .values. And we can see that they're the same. So this verifies that imputer works correctly as expected. Okay, so here comes the next important part of scikit-learn's libraries, which is the transform part. So as mentioned earlier, when we do .fit housing num, we are feeding our data into imputer. And when we do transform, this actually modifies our data set. So our data set, which is housing num, we feed into imputer, and then we transform it. So once we feed into imputer, nothing has been done to our data set at all. We don't have anything new. The values are still 0. They're still not a number. What it does is that it gives imputer the data so that it can calculate certain values like the statistics or the median values. Then over here, when we call transform, it goes into our data set and replaces all these missing values with the median. And it will store it inside X. So we create a housing transform, and we feed the pandas. We create a new pandas data frame, from X, because X is just a NumPy array. And we want to get back our data in the same form that we have. So we call this function, and we can, okay. So housing transform contains the transform data from X. And what we do here is we look at housing transform, we get all the rows that are incomplete. So this is a way to index all the rows that have incomplete values. Because sample incomplete rows give us all the rows that are incomplete, we look at their index and we get a list of their values, which we feed into, we locate them inside our housing transform. So as you can see, housing transform, similarly to the previous one, has total bedrooms filled in as 433.0. So what we did above and what we did here is the same thing. It's just that with scikit-learn, we actually get a lot more features if we do it the way that scikit-learn does. And it helps us to, it makes it easier to build a pipeline later on, which we will see. So just remember here, the takeaway is that you have your imputer class, which is from sklearn library. You have your fit and you have your transform. So the fit and transform is a very important part of like building a pipeline in scikit-learn. And there's also another thing called fit transform, which just applies these two together. So yeah. Okay, if we check out imputer strategy, it should be median. So this is the strategy that imputer uses to calculate what to fill the missing values with. Yeah. So this does the same thing, just that we're looking at the first 5 values. And as you can see, it'll be the same as the first 5 values of the data set. Okay, so that's it for filling in missing values. And we move on to handling text and categorical data. So over here, we get a data set, but we filter with only columns that have categorical data, which is ocean proximity. So if we look at the first 10 values, we get ocean proximity. So some of them are less than 1 hour to ocean, near ocean, inland, and inland. Yeah, less than 1 hour to ocean. So this are all in text. And as you know, your computer can't actually read text. So we need to transform them into a series of numbers that the computer can understand and carry out some algorithms to predict the value. Okay, so we'll look at how we can do that. So as you can see, this part is a bit similar to what we did above, where we imported something from sklearn pre-processing, and we're actually using it to fit transform our data. So notice that sklearn libraries, usually all their classes come with this fit and transform, which allows you to define like a pipeline of fitting and transforming your data. So when you have a data, you always fit it with something, and then you transform your data. So this is the process of what we call data transformation. And defining it this way gives you a very easy way to view your data and what is being applied to it. So at the start, we applied imputer. Now we applied this thing called the Ordinal Encoder. Okay, so let's look at what Ordinal Encoder does. Okay, so notice that we get a housing cat encoded actually gives us 0041010100. So what this means is that these values over here, they have actually been transformed into values 0 to 4. So if you look at categories, now we can see 0 corresponds to less than 1 hour to ocean. And if you look at the top, it corresponds to the first item as well. Now the third item, near ocean, the third item here is 4. And 4 is 0, 1, 2, 3, and 4, which is near ocean, which isn't correct actually. But let's see. Okay, so this transformation is not 1 to 1, and it's actually based on the sorted order of the frequency that they actually appear in. So if you look at the frequency that appeared above, okay, where is it? Oops. Yeah, so actually going by this frequency, and that's what Ordinal Encoder uses to define your categories. Okay, so moving on to, okay, so Ordinal Encoder encodes it from 0 to 1. So what we'll have in the end is one category, which is called ocean proximity, and these values, instead of being text, will just transform to 0, 1, 2, 3, or 4, any of those numbers. But what this does is that it gives an illusion, right, that values 0 and 1 are closer together than values 0 and 4. So if you look at this mapping, less than 1 hour to ocean and inland, they're actually quite far apart, right? If you look at it like on the map, because less than 1 to ocean should be closer to near ocean. But assume that this was labeled 0 and this labeled 4. So it kind of tricks our model into thinking that 0 and 4 are further apart than, let's say, 0 and 1. So this is something that arises when you use something like an ordinal encoder, which just encodes each text to 0, 1, 2, 3, or 4. So instead of using an ordinal encoder, we use something called a one-hot encoder. So what one-hot encoder does, okay, so as you can see, similarly, we have a class, we define fit transform, we feed our data inside, and we get the transform data out. So if you look at housing category, what this does instead of the above is that it transforms each one column into 5 columns. So you can imagine this as this, but if this right here says 0, it transforms to the first column here. And if this one says 4, it transforms it to the fifth one, which is 0, 1, 2, 3, and 4. So the third row here, 1 is on the fourth, is on the fifth column. So what one-hot encoding does is that it defines 5 columns. So your 5 columns can correspond to less than 1 hour to ocean, inland, island, near bay, and near ocean. This will instead become your column labels, and 1 will represent yes. So if this row belongs to less than 1 hour to ocean, a 1 will be placed under this column label. So as you can see, this one actually solves the problem that we had earlier, where values like less than 1 hour to ocean and inland could be thought of as like closer to each other, because this one might be 0, this one might be 1. And the distance is like 1, but compared to 1 hour to ocean and near ocean, the values of 0 and 4 make it seem further apart. And this solves that problem because of the fact that each category is its own column now. So it's only being compared to its own column. So 1 will compare to 0, and 1 here will compare to 0 here. So they'll be sort of like the same distance apart, no matter like which category they are in. Okay. So this is actually the same thing, but we'd just like to point out something which is called the sparse matrix. So when you have these arrays, when they are one-hot encoded, you will notice that you have a lot of zeros. So when you have a lot of zeros, they're actually called sparse matrices, and you can actually have a more efficient way to store it, which is called a sparse matrix. So this one is a more efficient way to store your data, and if you have a like huge data set, this one will take up less space. So imagine that you have like 10 categories. So this matrix will actually be like 20K times 10, which is like 200K values. So to store them more efficiently, scikit-learn actually gives you a sparse matrix. So you need to take note that if you want to turn this off, you can turn it off with sparse equals to false. But otherwise, it's the same thing. You just do fit and transform. Yeah, so we can look at the categories. Yep, so this will be the first column, second column, third column, fourth column, and fifth column. And if you look at housing.columns, so these are the origin columns. And now we notice that ocean proximity has been split into 1, 2, 3, 4, and 5 columns itself. And we won't handle like concatenating them together for now, because we'll actually define like custom pipeline to help us do that. Okay, so moving on. The next part is about custom transformers. So all these things that you have seen so far, one-hot encoding, imputer, and ordinal encoder, all of these are called your transformers, and scikit-learn provides all of them. So when we want to define like custom transformations to our project, we want it to in a way that works with scikit-learn. And how we can do this is by extending from these classes that scikit-learn provides you. So we define transformers to create these attributes that work seamlessly with scikit-learn functionalities. And what we need to do is create a class that implements fit and transform, and fit transform. But most of the time, you don't need to implement fit transform, because fit transform is just fitting, then transforming. So once we, if we want to make it work similar to how scikit-learn libraries work, all we need to do is define how fit works and define how transform works. Once we do this, our class will look like a scikit-learn class where we have to call fit, then we call transform. And by doing it this way, scikit-learn knows how to work with our data. So right now, we're importing scikit-learn libraries and we're using them ourselves, but scikit-learn has no idea how to use our libraries. So by defining our custom transformers this way, we tell scikit-learn how to work with our transformers. And in this way, it can actually help to speed up your entire pipeline and make it like more clean and very efficient. So we'll see how it works later on. But for the most part, what you need to do is import base estimator and transformer mix in. So what this first one does is, this is compulsory to tell scikit-learn that you're actually defining a transformer. This transformer mix in is not that useful. It just tells scikit-learn that fit transform will be a result of fit then transform. So you can do away with this, just that you will need to define fit transform later on. Okay. So let's look at the code one by one. So we import our libraries. Next one, we calculate the index of the columns. So this is just a line of code that help you get the index of the room ID, bedrooms ID, population ID, and household ID. Okay. So our class will be called combined attributes adder. So what we call it this is that, remember above when we added total rooms per household and total bedrooms per household, this is what we'll be defining this transformer to do right now. So instead of adding it ourselves, we will define a transformer that will transform our data based on what we tell it to do. Okay, so let's just continue. And so as we learned in our previous Python workshop, for every class you need to define the init, which is called the constructor. So this constructor is created whenever we initialize a class. So this is an initialization of a class, and this is where the constructor will be called. So over here we pass false inside, but the default value will be true. So in the constructor, what we do is we set this value, add bedrooms per room, and it will tell us whether we want to add this attribute in our data set at the end. We will define fit, passing itself, which all methods of a class must do, x, which is our data set, and y equals to none. So this is why sometimes it's needed inside your fit when you have labels. So y actually represents the labels of your data set, which are like the answers to your data set. And because we won't be using this, we'll just set y to none. So fit return self, because we won't be like doing any transformation or operating on anything in the data set when we fit it. What we only want is to transform the data. So fit is actually useless for us. Okay. So transform. Transform takes in x and y. Y will be none as well, because we won't need the answers in this case. Okay. So for rooms per household, we'll take x. Basically this part is just calculating, taking all the rows of rooms and dividing by like their household index. So we calculate rooms per household, then we calculate population per household. So this is all the rows of, this semicolon, this colon here represents all the rows, to take all the rows of this index. So the room index will represent the column, the index of the column of total rooms. And then we divide it by all the rows, but this time the household index, which will give us rooms per household. So similarly for population per household as well. Then remember in the constructor, we added this value, add bedrooms per room. So similarly, we will calculate bedrooms per room if needed. Okay. So after this, we return a numpy array with x. Okay, this thing concatenates x, your rooms per household, population per household, bedrooms per room. This is if add bedrooms per room is needed. If not, it just returns x, rooms per household, and population per household. So notice that we pass in maybe like a pandas data frame. We actually don't pass in the pandas data frame, because over here, if you look at what we pass in housing category. But housing category is actually taking only the values for ocean proximity. So we're not actually taking a pandas data frame anymore. We're just taking in the values over here. So what happens over here is that transformers always return you like a numpy array or an array. It doesn't always return you pandas data frame, because it's much simpler for scikit-learn itself to work with numpy arrays. And this is why for transformers, we'll actually be defining them to return numpy arrays instead. So what they take in can also be numpy arrays. So they take in numpy arrays and return you numpy arrays, and this can let you define a series of transformations, such that one transformer will transform data out. You feed it into the next transformer, and it output you another data set, which you can feed into another transformer as well. So using this, we can see that housing extra attributes will just be the same data set, except that we'll have a. Okay, let me just show you all how it looks. Okay, so notice that now we have extra values at the end, which is actually, this is actually the rooms per household, and this is actually the population per household. So notice that we put add bedrooms per room equals to false. So we don't have the third column and only 2 additional columns. Okay. So alternatively, instead of defining a whole class that extends from these two, we can do a function transformer, which lets us define a function that acts as a transformer. So calling this will act as you calling fit x, and then transform x. So this is actually just another way to do the same thing, which we won't actually go through in this, but we leave the code snippet here in case you want to look at it. So notice that if we pass function transformer the function, we actually can operate it on it the same way with fit transform. Okay, so at the end, we can look at housing extra attributes, which is what we obtain out here. We'll add the columns. Of our original data set plus room per household and population per household. And from this, we actually get our final pandas data frame, which looks like this. Okay, so the next part we'll move on to is feature scaling. And this is pretty important in data science because if we look at our distribution of data, we go all the way back up to here. We can see that this distribution is quite tail heavy. Like it starts up sharp, goes up, and then a lot of values are concentrated at the end. So you can see that they don't actually end how they finish. And this is like a source of problem that we can actually rectify with some scaling that we do with our data. So there's some ways to do scaling. And yep. Okay, so okay, another reason why we need to do scaling is that some of input numerical attributes have different scales. So the total number of rooms range from 6 to 39320. So you can think of this total rooms from like having a large range and values way above 10. But the median income only ranges from 0 to 15. So median income is like a float number, and it actually ranges from 0 to 15. And what this may cause is that what this could result in is that larger values get higher weight and they affect our data more. So this would indirectly cause our model to think that total number of rooms are more important than the median income, which is not what we want. So there are two common ways, and we do min-max scaling and standardization. So we're actually doing standard scalar, which is standardization. And okay, so let's just go through min-max scaling. So values are shifted and rescaled, so they end up ranging from 0 to 1. So instead of having a range from 6 to 39K or 0 to 15, every single data will have a scale from 0 to 1. And we subtract the mean value and divide by max minus the mean. So scikit-learn provides transformer. So transformers, as we learn, we can just do fit and transform. And standardization is different, where it subtracts the mean value first and divides by the variance. So again, scikit-learn provides a transformer called standard scalar. And this is how we can fit into our pipeline. Okay, so we won't actually fit. Okay, we'll see how we can fit this on pipeline later on. So now what we're doing is we're defining a pipeline, and this pipeline is just a series of transformation of data. So from the data that we get at the start when we download it from GitHub, we apply a series of transformations through these classes until we can until the data is ready for us to process in our model. So what we need to do for our data is fill in the missing values to the median, add our custom attribute, which is the rooms per household, and lastly, apply feature scaling. So notice that this is only for the numerical attributes, and we won't be handling the categorical attributes yet. Okay, so we import pipeline from scikit-learn and also standard scalar, which is the one that will give us standardization in our model. Okay, so notice that we have all these classes like simple imputer and standard scalar, which we imported from scikit-learn. And notice also over here, we have function transformer add extra features. So this can actually be replaced with this. So okay, we can actually replace this with our class that we defined previously, or we could use the alternate method, which I'll just run here so we can get it in our Google Colabs. So we define our pipeline as a list of transformations we want to add. So what we do is we provide a list. Each element of the list contains the name of the step of the pipeline, which is imputer, and we'll take in simple imputer, which is the class that applies on transformation. Next one is our attributes adder, and we pass in our function transformer that adds in extra values, extra features. Lastly, we'll do standard scaler, which applies the standard scaler transformer onto our data set. Now, we can see that NumPipe, once we define this pipeline, it gives us a very similar API as what the classes did, which is feed transform. So when we call NumPipeline feed transform and we pass in our data set, what this actually does is that it goes through the list. The first one is imputer, and it'll feed our housing num into simple imputer, call feed transform, get the output of simple imputer, and feed into our next one. So it's the same as calling this. So the same as calling like our imputer. Same as calling this, and then we have this, which is attributes adder, and we pass in x. And the next one is x equals to standard scaler. Okay, so when we call this line, what we're actually doing is all of this. But this gives us a simple way to see what's in our pipeline, what transformations we're applying to it, and add names to them. So in the future, when we are actually like, when we're doing the same project, we can just import this pipeline and use this pipeline instead of all these values that we have to use. So you can see how defining custom transformers in the method that scikit-learn expects will help us to like make our code cleaner and actually more reusable in a sense. Okay, so after we transform it, we can see that what we did. Oops. Okay, so after we apply the transformations, we can see the data is also a NumPy array, because remember that feed transform gives us NumPy arrays. And these are actually all the values, but they have been applied, they have been filled in, the empty values are filled in, the new attributes are added, and they have been scaled down by standard scaler. Okay. So another way that you can do this, okay, this is not another way, but if you want to apply transformations differently, in the sense that you have your numerical data and categorical data, we need to define different pipelines to each column. So the columns that have numerical data will go through what we call the num pipeline, and the one with categorical data, we go through one-hot encoding. So note that the categorical data will not go through the num pipeline, and the numerical data does not go through one-hot encoding. So this feature by sklearn called column transformer is something that helps you handle this nicely. So as you can see, number of attributes, we get the list of all the columns that are numerical. Categorical attributes is just ocean proximity. And the full pipeline, we apply num pipeline to numerical values, one-hot encoding to the categorical attributes. And again, the pipeline has the same API, which is feed transform. So this is like, we can use the same function in all of sklearn. And it gives us like a way to expect how we can work with data. So if we can see some function has something that's feed transform, we can likely guess that we can pass in any data set, and we can expect like a NumPy array back. So we run this through, and we look at housing prepared. So note that now the last few values are 0 and 1s. And this corresponds to the one-hot encoding that we have defined for our categorical data. And we look at the shape. So initially we had, okay, I'm not sure how many we had at the start, but now we have a lot more based on the one-hot encoding, and as well as the extra attributes that we added in. Okay, so over here, we're moving on to some housekeeping steps, which will make our entire process a lot more streamlined. So we define a custom transformer again that gives us the value that we need given a list of column names. So this one allows us to replicate the same process in terms of pipelines. So what I mean by this is that all data frame selector is a class that we define. We pass in attribute names, and you'll select those names, those attributes out from the dataset. So num attributes and cat attributes, instead of defining it this way, where we pass in the attributes themselves directly, we pass into the data frame selector. So it will select the data from the data frame, which is our housing data frame, and then pass it through the pipeline. So, okay. This is really just like a helper function you can just copy paste and use inside your projects, because this is defined in a lot of projects and you can actually just take it and use it. So there's not really a point in like learning what this does. It's something that can make your code neater and something that a lot of people will use to make it make their code more streamlined. So again, this is not compulsory, but it's like a nice to have thing. Okay, so what happens after this step is that instead of having to use this column transformer, we now have two separate pipelines. So one pipeline will be what the numerical attributes have to go through. The categorical one will go through this pipeline instead. And we use feature union to add them together at the end. So remember, we have two pipelines, and then we have this feature union. So this feature union will have the data from this pipeline and the data from this pipeline, and you add them together. So you can see this is exactly the same thing that we had previously. So it's exactly the same method. It's just a different way of doing it, and it's up to your personal preference which one you think will work better for you. So a lot of people like the pipeline way because defining a pipeline is more reusable in a sense compared to a column transformer where these columns may vary throughout like different runs. So this pipeline method, more people prefer this way. Okay, so actually we're at 8:52. I think we can take a short break right now, and when we come back, we'll actually get into predicting our housing values and how we can improve upon them. So we'll take a short break and we'll come back about 9:10. Hey guys, it's 9:10 and we'll resume with the workshop. So we're actually at the last part, and from this on, it will just be how we train a model, how we select a model, and how we actually evaluate like different metrics on the model and what we can do to improve this model in the end. Okay, so to summarize what we did, we got the data, we explored the data, we sampled like a training set and test set. We only looked at the training set so far, and we wrote transformation pipelines to clean up and prepare our data for machine learning algorithms. So this transformation pipeline, as you recall, is part of this feature union thing, where we have one pipeline for the numerical data and one pipeline for the categorical data. Okay, so let me just run all this code. Okay, so now, now all we need, this is actually all that it takes for us to create a working model. And the first model that we're looking at is linear regression. So linear regression, you can think of it as just like plotting a straight line through all your points, like the best fit line. And that's how we will be able to obtain our predictions. Okay, so notice that something really cool about this model, which is that it follows the scikit-learn methodology of using fit and transform. So notice that transforms your data. So from from your initial data set, you get something different. Now what fit does is that it doesn't transform your data, it doesn't change anything. But when you call fit on this kind of classes, it actually gives them, it allows them to calculate certain like data that they need. So for example, in the case of a best fit graph, you have your gradient and you have your y-intercept. So when you call fit, you can think of this as calculating the gradient and the y-intercept given all your data points and the labels. So something different here as well is that there's actually a labels in this part where we didn't have labels before. So we only passed in the data, but now we also pass in the labels or the answers to our data set. So row 1 should evaluate to maybe like 200K house price. Row 2 should maybe evaluate to about 300K of house price. And when we call fit on linear regression, it will actually calculate all the values that it needs to do a prediction on your data. Okay. So let's try the full like pipeline on a few instances. And okay, so what we're doing here is we're actually getting the first 5 values from the housing, from the data. The first 5 values from our labels, and we put them through the full transformation pipeline. So this full pipeline will transform our data, and our data that we prepared will actually be will be passed into linear regression to predict. So you can think of some data prepared as the data without the labels. So maybe like, okay, I'll just show you what it actually has. Okay, so some data is actually all this line of data. And notice that this is the original data set without any transformations. We still have ocean proximity as a categorical data with text inside. And we don't have our extra attributes that we added in the end. And notice that none of these features are scaled. But over here, we actually transform it inside our pipeline. And it's now inside some data prepared. So if we look at some data prepared, we can see that it's actually has been scaled. We have our extra one-hot encoding over here. And we also have filling like missing values and everything that we have defined in our pipeline. So now we ask for linear regression to predict the housing prices of these houses given their data. And we get predictions of like 210K, 300K. And these are what our model has output as predictions. So if you look at the labels, which are actually the answers, we can see that the values are a bit off. And it's about different from maybe like 70K difference here and 30K difference here. So it's a bit troublesome to keep looking at all these values one by one and see how much like the difference is. So maybe like this difference is only 20K, but this difference over here is 70K and it's like way larger. So it's hard to keep track of everything that we have seen so far. So what we need is some metric to actually define how well it performed. So one metric that we can use is called the mean squared error. So it takes the error, how far off we are, and it squares it. So what the squaring does is that it penalizes greater deviations from the original label more. So larger values, when you square it, you get an even larger value, and smaller values, when you square it, it's not as the increase in size won't be as large as larger values. So this actually penalizes your model when it makes very large mistakes. Okay, so how we do it is that we have our predictions, which we predict by using the entire housing prepared dataset. And we calculate the mean square error through this function, where we pass in the labels, where these are the true answers, and our predictions. So we'll calculate our error based on this too. Okay, so as so this actually calculates the mean squared error, and we get the root mean square error to get like a positive value. Okay, so notice that this is in terms of error. So when we're talking about error, a larger value is worse because that means your error is larger. So this value of like 68K means that our error is like, okay, we actually can't really tell how good this performs. But if you look at our data set, our prices are in the range of like some 0 to maybe 500K. So we can take a look at this 68K. We can think it's actually a very high value compared to like the range of values. So you can sort of think that this model doesn't seem to be very accurate so far. So other metrics can be imported. It's called the mean absolute error from SK matrix. And we do it the same way. We pass in our predictions and we pass in the labels and it calculates the error. So this error is calculated throughout the entire data set, and we actually see that the absolute error is less. So it's likely that we're actually performing a lot of our errors have very large deviations from like the actual answers, which is why it's being penalized more in mean squared errors. Okay. So as you can see, most median housing values range from like 120K to 265K. So our prediction error of like 68K over here is not very satisfying. So this is an example of a model that underfits the data. So the features do not provide enough information to make good predictions, or the model is not powerful enough. So it's one of these two cases. And as you can see, to improve upon it, we can actually get more features. We can like engineer more features for the model to learn from, or it just means that the model isn't good enough. So the two ways we can improve upon this is one, to get more features, or two, get a more powerful model. Okay. So let's try like a one. Okay. So let's try with a different model and we see how it performs. So this next model that we're using is called a decision tree regressor. So a decision tree looks at your data and it decides at each point whether like it splits your data in terms of like binary points and decides whether what features will result in what additions to the predictions you need to make. So you can think of it as a tree, and like the leaves of the tree will be like the range of predictions they will give. So we give this is how we initialize our decision tree regressor. So it's the same way as the linear regression, as you can see. We initialize the class, and then we fit it. So over here, we define a class, and now notice that we have to pass in something called a random state. So this random state is because the decision tree regressor actually relies on like random values inside. So by giving it a random state, we can ensure that this performance of the model can be replicated in future runs. And as usual, we fit it with the prepared values and the labels. Okay. So now we're using mean square error, and we'll actually calculate the error for the tree. Okay. So you can see that this error is actually 0. So compared to 68K, it seems like a huge improvement. But notice that the previous problem that we encountered is when the model underfits the training data. So our model wasn't strong enough to like handle all the features that we fed it, or it could mean that the features are not representative of our data, and we can't actually use the features that well. So this is the opposite case, where our model has barely overfit the data. So what this means is that our model didn't actually give us accurate predictions. It just memorized the entire data set. So it just memorized that these features will lead to this kind of output, and it just outputs the same. It went through the training set and keeps memorizing it. So as you can see, this is why we don't want to touch the test set until we're ready to launch a model. Because imagine if you give it the test set, like your entire data set, and it just memorizes your entire data set. And this way, you can actually measure how well it will perform on data it has not seen, since it has seen all the data in your data set. And this is why the test set is important, so now we can use it as part of evaluation and for model validation. Okay, so over here, we have defined our evaluation metrics on one particular subset of training set and one subset of test set. Now, to make it better, we can actually get multiple training sets. Like we split 80% this way and another type of 80%, like with different indexes. And this is actually a way we can average out all of these errors to give us a more accurate error. So this is actually called cross-validation. And we can randomly split the training set into 10 distinct subsets called folds. And it trains and evaluates the model 10 times, picking a different fold for evaluation every time and training on the other 9 folds. So what this means is that it will look at 90% of this data set and evaluate on the last 10%, which it has not seen. Then it will train on another different 9 folds and evaluate on the last fold. So this way we get actually like 10 predictions, and we take the average, it's more accurate. So how we do this is we import cross-validation score. And it's quite simple. We pass in the model we want to use, our data to evaluate on, and the answers. So we pass in the scoring, which is negative mean error square, negative mean square error. So it's the same metric as above, it's just that it's negative. And CV is the cross-validation, so we want 10 folds because we want 10 distinct subsets. So we can pass in different values, and it actually give you different sizes of your folds that you use. So we calculate the 3 root mean square error, the scores. And scores is actually consists okay, so scores actually consists of like a mean and a standard deviation, which we can print out using this helper function. Okay, so we can see that the scores are this, and the mean score is about 71K. So already you can see that it's better than 0 because 0 doesn't tell us anything, and it actually performs worse on data it has not seen before. So for 0, it's actually seen all the data that he has already that it's already seen all the data, and that's why it's able to overfit and memorize all the data. But when it doesn't get a chance to look at all the data, it performs way worse. It performs way worse, and it actually is even worse than linear regression. So if we can actually calculate the one for linear regression using the same way, we get a mean of 69K, and it's actually a bit better than the root mean square for the tree. So cross-validation is a better way to evaluate your models because it takes the average of multiple runs and makes it just more accurate in the end. And also, you are evaluating on data that it has not seen before, rather than data that is already seen and has a chance to memorize this data. Yeah. So yeah, cross-validation is a better way for evaluation, and you should always almost use this. You should almost every single time you are doing evaluation, you should use cross-validation. Okay, so the last part of our notebook is a bit of something to do with luck, and depends on how much resources and time you have. So we can actually fine-tune hyperparameters. So if you notice here, we can actually pass in random state to decision tree regressor, and there are multiple more things that you can pass in, like CCP alpha, max features, max leaf nodes, mean impurity decrease, and all this. If you mess with all these settings, you can actually get better or worse performance. So, okay, so now we'll look at a different model. It's called random forest regressor, and similarly, it will give us predictions of our housing values. And what will enable us to carry out this fine-tuning of hyperparameters is something called grid search CV. What grid search CV does is that you give it some parameters you want to iterate on. Like for n estimators, I want to test values of 3, 10, and 30. Max features, I want to test features, max features of 2, 4, 6, 8. Bootstrap, false, and estimators 3 and 10. Max features 2, 3, and 4. So these are the grids that you iterate upon. And how you can look at all these parameters that you can change is you go to the documentation page and look at random forest regressor. So this is what we are using right now. And over here, under parameters, you can see that there's n estimators. You have max features, max leaf nodes, bootstrap, which we actually define. And what else did we do? N estimated, yeah. So we just have this tree. Okay, so what this grid does is that it takes the first grid to search. And what it will do is that you initialize random forest regressor with 3, n estimators of 3, max features of 2. It will evaluate the data set on the housing labels, and then the next you'll do it again, but this time with n estimators of 3, max features of 4. So you try all possible combinations of your parameters, and after that it'll tell you the best one. So over here, we initialize our regressor, and we call grid search CV. So grid search CV, we pass in the regressor that we're using, the parameters we want it to iterate on, and this CV is a cross-validation value, which is what you use to evaluate our model. So you can see that for each pair of parameters, like maybe 3 and 2 here, it's actually doing the test 5 times. So it actually, if your model is huge and your data set is huge, it will actually take you a very long time to iterate through all this. So this is why fine-tuning hyperparameters is something like it really takes a lot of time and resources. And you could start, it's better to start early, or you can actually look at other things like getting more features out of your data set or getting better data in general, which would improve the results more than trying to like get the best parameters for your data set. So also another thing to know is that this may always help. So if you really have nothing else to do, this is probably your best bet. Okay, so let's see how it works. Now, again, scikit-learn provides us like a very good API. So we just have to call .fit, pass it the prepared, and pass it the labels. So you can see it's taking quite a while to run. It's because it's iterate through like a lot of parameters. So when this is done, what we can do is we can obtain the best parameters through grid search.bestparams. And you'll just give us like the best parameters that it discovered throughout its iterations. Okay, so just wait for this to run. And also you can note that we put bootstrap here to false when its default value is true over here. So basically, for this first grid, all the bootstrap values are true, and the second grid, all the bootstrap values are false. So it actually tells us which is better, to have like false bootstrap or true bootstrap. Yeah. So while it's still running, another thing you can look at to getting a model. Okay, actually it finished. Okay, so we can run best params, and we see that it tells us the best parameters are when max features is 6 and n estimators are 10. Okay, so we can actually verify that this is true by doing by creating two models over here. So first one, forest regression, bad. We expect it to have worse output. We put max features 2 and n estimators 10. So this is different from the best parameters that we can have. For forest regression, good. We have max features 6 and n estimators at 30. So these are the best parameters you can have. And we expect the good to perform better than the bad. So we run bad, we get a root mean square error of 23K. So notice that this actually performed better than our previous two, decision tree and linear regression. And the good one actually gets an error of 19K. So we get a slight performance benefit just through the use of like tuning our hyperparameters. So this again is a search that takes a lot of time because there are so many combinations of attributes you can use. So there's so many values over here, and these are actually integer values or float values. So really you could go up to maybe like 300 with all this, and you need to decide what are the increments you want to add. So maybe you can do like 3, maybe like 1, 10, 20, 30, 40, 50, and you go on forever until like maybe 200K. And what's really the best method to do here is to go by powers. So over here, maybe you could have 2, 4, 8, 16. And over here, you have like 1, 10, 100, 1000. So by doing in powers, you start to narrow down your search. So let's say you iterate from, let's say, from 1, 10, 100, 1000, and then 10,000. And second one is also similarly the same. So let's say you do this and you get that your best value is actually 1000, right? So now it makes it easier. Because the thing is, you can take this range from 100 to 10,000 and you repeat your search within this smaller range to get like a final search. So you start with a very coarse search. You search like huge values, like a range of huge values. You start to slowly narrow it down. And this is how you can like try to optimize the way you search for hyperparameters. But again, this will still take you like a lot of time, and it's better to start early. And it's really hard to decide when you should start tuning hyperparameters, because the other options you can choose is that you can choose other models, or you can look at your data again and try to engineer more features in your data set. So yeah, again, it really depends up to you, and you have to spend a lot of time and like experience, like practical experience with all these different data sets to know what's the best to do at each point. So the best is to get more practice and keep practicing on different data sets. Look at what works best for this data set and try to learn why this particular case, this is the case for this data set. So example would be like learning why max features of 6 and 30 seems to work better for a kind of data set like this. Yep. So that's actually the end of our workshop. And if you have any questions, we can answer them. You can ask them and we'll answer.
Yeah, actually, guys, does anyone have any more questions or any feedback? Feel free to voice it out. Now you can unmute yourself or you can just type in the chat. Okay, if yeah, if you guys have no questions, right? Just one last thing. We will need you guys to turn on your cameras because we want to take a group photo. Yeah. So everyone that's here, just help me turn on your cameras and smile, of course.
I can stop screen sharing so you can take the photo. Thank you.
Okay, guys. So I guess we're done for today, lah. Does anyone have any more questions? Yeah. Okay. If not, I think we'll end it here for today, lah. Yeah. Good job, guys. Thank you.